Hello everybody, welcome into another lesson. So today we are going to verify other types of trig identities. And for the first part of the lesson, we're going to use periodic identities of trig functions to find the exact value of some equations. So we want to find the exact value of the sine squared of 35 degrees plus the sine squared of 55 degrees. And you're looking at this, you're probably thinking, how am I going to find the exact values? We're going to get some very hideous decimals and we're going to have to round. Well, okay. Let's consider something here. You have 35 and 55. Together, don't they add up to 90? They certainly do. If we remember the periodic identities of cofunctions, that sine of 55 degrees, isn't that going to be the same as the cosine of 90 degrees minus 55 degrees? Because a function has a period of 90 and it makes it the cofunction. So the sine of 55 degrees is the exact same thing as the cosine of 35 degrees when you subtract it from 90. So we can now turn this into the sine squared of 35 degrees plus the cosine squared of 35 degrees, which sine squared plus cosine squared using the Pythagorean identity gives us 1. So we should get an exact answer of 1 from this. So understanding your periodic and Pythagorean identities are absolutely critical. A similar problem, we have the cosine squared of 14 degrees plus the cosine squared of 76 degrees. Well, okay, we have 14 and 76. We know together that 14 and 76 add up to 90. Now, the cosine squared of 76 degrees, we can deal with the 76 because if you take the sine of 76 minus 90, you can use the periodic identity and turn this into the sine squared of 14 degrees. So this would actually turn into the cosine squared of 14 degrees plus the sine squared of 14 degrees, and cosine plus sine, the squared of each equals 1. So you actually should end up getting an answer of 1. Two more of these, then we're going to move on to some logarithmic trig identities. So we are now given the cosine squared of 20 degrees plus the cosine squared of 52 degrees plus the cosine squared of 38 degrees plus the cosine squared of 70 degrees. Okay, so how are you going to approach something like this? So you have the cosine squared of 20 degrees plus the cosine squared of 52 degrees plus the cosine squared of 38 degrees plus the cosine squared of 70 degrees. Well, you know if you add 20 and 70 you get 90. If you add 52 and 38 you get 90. So the first thing I would do is put the respective two angles that add up to 90 close to each other. So we can rewrite this as the cosine squared of 20 degrees plus the cosine squared of 70 degrees plus the cosine squared of 52 degrees plus the cosine squared of 38 degrees. Get these two sums of 90 close together, and then you can use the periodic cofunction identities. So cosine of 70, that's going to be the same as the sine of 20, right? So this could turn into the cosine squared of 20 degrees plus the sine squared of 20 degrees. Plus, now you have the cosine squared of 52 plus the cosine squared of 38. Well, 52 and 38 also equal 90. You can use the periodic identity for that cosine of 38. You would get that it's the sine of 52. So this would be plus the cosine squared of 52 degrees plus the sine squared of 52 degrees. Now you have something you can work with. You have the Pythagorean identities. So if you look at the first two terms, cosine squared of 20 plus sine squared of 20, that's going to be 1, plus if you take your cosine squared of 52 plus the sine squared of 52, that's another 1. So this turns into 1 plus 1, which should end up giving you an answer of 2. So the exact value you should get is 2. One more of these. Alright, so we have the sine squared of 18 degrees plus the sine squared of 40 degrees plus the sine squared of 50 degrees plus the sine squared of 72 degrees. Alright. So the sine squared of 18 degrees plus the sine squared of 40 degrees plus the sine squared of 50 degrees plus the sine squared of 72 degrees. So if you look at 40 and 50, those add up to 90. Keep those together. But then you have 18 and 72 that are separated, but 18 and 72 add up to 90. So the first thing I would do is regroup these together with their respective sums of 90. So I would rewrite this as sine squared of 18 degrees plus, bring that sine squared of 72 degrees over here, and then you can keep your 40s and 50 together. So this would be plus the sine squared of 40 degrees plus the sine squared of 50 degrees. Alright, now that we got these together, let's look at 18 and 72. Well, the sine of 72, if you make this the cosine of 90 minus 72 using the periodic identity, you would get the cosine of 18. So this would turn into the sine squared of 18 degrees plus the cosine squared of 18 degrees. Plus, let's look at your 40s and 50s here. So if you use the sine squared of 50, so the sine of 50 is the same as the cosine of 90 minus 50, which would give you the cosine squared of 40. So this would turn into plus the sine squared of 40 degrees plus the cosine squared of 40 degrees. Now you can default to the Pythagorean identities. Look at your first two terms. Sine squared of 18 plus cosine squared of 18 is 1. Plus look at your second two terms. Sine squared of 40 plus cosine squared of 40 is 1. So you're left with 1 plus 1, which should give you an answer of 2. So that one also really isn't that bad. These may look hideous in the beginning, but if you understand the periodic and the Pythagorean identities, these really aren't that bad. Okay. So those are using Pythagorean and periodic identities to solve equations. Let's shift into verifying logarithmic trig identities. So we have to verify that the natural log of the cotangent of theta is equal to the natural log, the absolute value, the natural log of the absolute value of the cotangent of theta equals the natural log of the absolute value of the cosine of theta minus the natural log of the absolute value of the sine of theta. We have to verify that. Okay. So believe it or not, logarithmic trig expressions come up all the time in calculus, especially in Calc 2. That's where you're going to heavily deal with them. And of course in differential equations and beyond. But why do we have an absolute value sign on these? Well, for one, you have to make sure that you don't get a negative value for your logarithms, because the logarithms aren't defined for a domain that's negative. It's only defined for greater than 0. As far as 0 itself, we know that we can't have a value that equals 0. So that's understood for logarithms, but you definitely, for all other values, you don't want a chance getting a negative inside your logarithm. That's why the absolute value is there. Okay. So start out writing your left-hand side, the natural log of the cotangent of theta. Well, we can keep the natural log, but what is that cotangent of theta? That's the same as the cosine of theta all over the sine of theta. Well, now we have turned this into a quotient rule with the logarithms, which is a difference of two logs. So this would separate into the natural log of the absolute value of the cosine of theta minus the natural log of the absolute value of the sine of theta. So we can say, therefore, the natural log of the cotangent of theta is equal to the natural log of the cosine of theta minus the natural log of the sine of theta. So again, these logarithmic identities are going to come up all the time in calculus, so these are very important. Three more of these, then we're going to move on again. All right, so we want to verify that the natural log of the secant of theta equals the negative natural log of the cosine of theta. So we have to verify that the natural log of the secant of theta equals the negative natural log of the cosine of theta. Well, let's write out the left-hand side. You have the natural log of the secant of theta. Whoops, not CO. What the heck is that? Secant of theta. Alright, so what is the secant of theta? That's the natural log of 1 over the cosine of theta. Well, okay, you have a reciprocal rule in the natural log. This can be the same as the natural log of the absolute value of the cosine of theta to the negative first power, not to be confused with the inverse function. We want to make that very clear. Now, what does the power rule say for logarithms? For logarithms, you can bring that power out front. So this would just turn into negative 1 times the natural log of the cosine of theta, or simply negative natural log of the absolute value of the cosine of theta. I'm always dropping something, man. Okay, so we've proven the identity, so now we can say, therefore, the natural log of the secant of theta equals the negative natural log of the cosine of theta. I got two more logarithmic ones, then we're going to move on to simplifying some trig expressions. Alright, so we got to verify that the negative of the natural log of 1 plus the cosine of theta is equal to the natural log of 1 minus the cosine of theta. This one's going to be a bit more of a doozy. Minus 2 times the natural log of the sine of the absolute value of the sine of theta. Okay, so this one's going to be a bit fun. We have the negative of the natural log of the quantity of 1 plus the cosine of theta. We have to verify that it's equal to the natural log of the quantity of 1 minus the cosine of theta minus 2 times the natural log of the absolute value of the sine of theta. Well, let's start out with the left-hand side. We have negative of the natural log of 1 plus cosine of theta. Well, when we have any coefficient on the natural log, that's the same as the power rule, right? So we can write this as the natural log of 1 plus the cosine of theta raised to the negative first power. Well, what is something to the negative first power? That's the natural log of 1 over 1 plus the cosine of theta to the positive first power. Okay, so what you have now is you have a sum of a trig expression in the denominator. Well, what do we want to do with that? We want to rationalize it because we don't want to leave our denominator with a sum of a trig expression. So to rationalize, you got to multiply the numerator and denominator by the conjugate, which would be 1 minus the cosine of theta. So this would turn into the natural log of 1 minus the cosine of theta all over 1 minus cosine squared of theta. Well, we can simplify this further. This is going to turn into the natural log of 1 minus the cosine of theta all over that 1 minus cosine squared turns into the sine squared of theta. Okay, well, if you have a quotient inside of a log, that's the same as the difference of the two logs. The difference of the log of the numerator minus the log of the denominator. So this is going to turn into the natural log of 1 minus the cosine of theta minus the natural log of the sine squared of theta. Well, again now, the sine is to the second power. We have a power rule on a log. So this is going to equal the natural log of 1 minus the cosine of theta minus, that power comes out front, so minus 2 times the natural log of the absolute value of the sine of theta. So we have just verified this identity. So therefore, we can say that negative of the natural log of 1 plus the cosine of theta is equal to the natural log of 1 minus cosine of theta minus 2 times the natural log of the sine of theta. So yes, that one was probably a bit more of a doozy, but if you understand the properties of logs, that also helps you. I got one more of these, then we're going to move on to simplifying some expressions here. Alright, so we have to verify that the negative of the natural log of the cosecant of theta plus the cotangent of theta equals the natural log of the cosecant of theta minus the cotangent of theta. This one actually comes up all the time in calculus, this one especially. So we're going to verify that the negative natural log of the cosecant of theta plus the cotangent of theta equals the positive natural log of the cosecant of theta minus the cotangent of theta. So let's start writing out the left-hand side. Negative natural log of the absolute value of the cosecant of theta plus the cotangent of theta. Well, again, you have a coefficient on the natural log, so this turns into the power rule. This is going to be the same as the natural log of the absolute value of the quantity of the cosecant of theta plus the cotangent of theta raised to the negative first power by the power rule of logarithms. Okay, now I'm going to keep writing over here because this is going to be a big one. Something to the negative first is the same as the reciprocal of this to the positive first. So this would be the natural log of the absolute value of 1 over the cosecant of theta plus the cotangent of theta. Well, here's the thing. We have the sum of two trig expressions in the denominator. We don't want that. We want to get rid of that, so we need to rationalize. So multiply numerator and denominator by the conjugate. So that would be the cosecant of theta minus the cotangent of theta all over the cosecant of theta minus the cotangent of theta. Alright, so now let's do the work here. The natural log of multiply the numerators, you'll literally get the cosecant of theta minus the cotangent of theta all over the denominator. If you FOIL that out, you'll get the cosecant squared of theta minus the cotangent squared of theta. Well, this is actually about to simplify. What is cosecant squared minus cotangent squared? That just turns into 1. So literally, you'll end up with the natural log of the absolute value of the cosecant of theta minus the cotangent of theta. So we have just verified the identity. So therefore, the negative natural log of the absolute value of the cosecant of theta plus the cotangent of theta equals the positive natural log of the absolute value of the cosecant of theta minus the cotangent of theta. Alright, so that's the logarithmic trig function verifications. So we are going to verify some reduced power identities, which also come up in calculus all the time. Then after these next 4 exercises, we're actually going to verify some inverse trig identities. We'll do 4 of those. So we want to verify that the tangent to the 5th power of x, tangent 5 of x, is equal to tangent cubed of x, secant squared of x, minus the tangent cubed of x. Alright, so we got to verify that the tangent to the 5th of x equals the tangent cubed of x secant squared of x minus tangent cubed of x. So, and again, these type come up in calculus all the time. So let's start with the left-hand side. Tangent 5 of x. Well, how can we simplify the tangent 5 of x? This isn't as bad as you think. Isn't this going to be the same thing as the tangent cubed of x times the tangent squared of x. If you take the tangent cubed of x times the tangent squared of x, you'll get the tangent fifth of x. So that's actually not that bad. Now, we can simplify the right-hand side further. We'll keep that tangent cubed of x. Now, what is tangent squared? Isn't that the same thing as the secant squared of x minus 1? So this would turn into the secant squared of x minus 1, which if you just distribute this, you'll end up getting the tangent cubed of x, secant squared of x, minus the tangent cubed of x. So that actually wasn't too bad. So therefore, we can say that the tangent 5 of x is equal to the tangent cube of x, secant squared of x, minus tangent cube of x. All right. Got 3 more of these, then we're going to do some inverse trig ones. We got to verify that secant 4 of x, tangent squared of x, is equal to the tangent squared of x plus the tangent 4 of x times the secant squared of x. So this one looks pretty bad, but we want to verify that the secant 4 of x tangent squared of x equals the tangent squared of x plus tangent 4 of x times the secant squared of x. Okay, well, what I'm going to suggest then is, let's start with the left-hand side. So we have the secant 4 of x times the tangent squared of x. Now we want to simplify this, but the right-hand side can kind of give you a framework of what you need to do to get there. What I'm going to suggest here is that you split that secant 4 of x into 2 secant squared of x's. So this would turn into the secant squared of x times the secant squared of x times the tangent squared of x. There's a reason for that. Okay. Well, keep your first secant squared of x the way it is. But what about your second secant squared of x? Isn't it true that secant squared of x is the same as 1 plus tangent squared of x? You would have that then times the tangent squared of x. Now you leave your secant squared of x alone. Now distribute that tangent squared of x, you'll end up times the tangent squared of x plus the tangent fourth of x. Which you can just rewrite this as the quantity of the tangent squared of x plus the tangent 4 of x. All that times the secant squared of x. So we have just verified the identity, therefore the secant 4 of x tangent squared of x is equal to the quantity of the tangent squared of x plus the tangent 4 of x, all that times the secant squared of x. Two more of these types. And then we do 4 inverse trigs, and then we'll do 4 trig substitutions, and then we'll be done with the lesson. All right. So we have cosine 3 of x sine 2 of x is equal to sine 2 of x minus sine 4 of x times cosine of x. Alright, so we got to verify that the cosine 3 of x times sine squared of x equals sine squared of x minus sine 4 of x times the cosine of x. So let's start with the left-hand side again. So the cosine cubed of x times that sine squared of x, let's set that equal to, okay, well, again, the right-hand side gives you a framework. It definitely would show that we should factor out a single cosine of x. So we can turn this into the cosine of x times the cosine squared of x times the sine squared of x. Well, now that cosine squared of x, that's the exact same thing as 1 minus sine squared of x. So this would turn into the cosine of x times 1 minus sine squared of x times the sine squared of x. So now you distribute that sine squared of x through your parentheses, you end up getting the cosine of x times the quantity of the sine squared of x minus sine 4 of x. Which would equal, then we can redistribute this. Sorry, I heard a funny sound for a second. I want to make sure everything was okay. So sine squared of x minus sine 4 of x times the cosine of x. So therefore, we can say that cosine 3 of x sine squared of x is equal to the quantity of the sine squared of x minus sine 4 of x times the cosine of x. One more of these, then we'll go on to 4 inverse trig ones. Alright, so we're being asked to verify that the sine 4 of x plus the cosine 4 of x is equal to 1 minus 2 cosine squared of x plus 2 cosine 4 of x. Alright, so we have to verify then that the sine 4 of x plus cosine 4 of x equals 1 minus 2 cosine squared of x plus 2 cosine 4 of x. Well, this should give us on the right-hand side a framework that basically everything needs to be in terms of cosines. So let's start here with the left-hand side. Sine 4 of x plus cosine 4 of x. Alright, well, let's deal with that sine. Isn't the sine 4 of x the same as the sine squared of x squared? So you could say sine 2 of x squared plus the cosine 4 of x. Well, now what is sine squared? That's going to be the quantity of 1 minus cosine squared of x, but this time that quantity is squared plus the cosine 4 of x. Well, now we just raise this binomial to the second power. That'll be 1 minus 2 cosine squared of x plus cosine 4 of x plus another cosine 4 of x, which would simplify into 1 minus 2 cosine squared of x plus 2 cosine 4 of x. So therefore, we can say that sine 4 of x plus cosine 4 of x is going to be equal to 1 minus 2 cosine squared of x plus 2 cosine 4 of x. Alright, so there's those for simplifying. Now let's do some inverse trig identities. Alright. We're going to verify. What we're verifying first is that the tangent of the sine inverse of x is equal to x all over the square root of 1 minus x squared. So we have to verify that the tangent of the sine inverse of x equals x over the square root of 1 minus x squared. Whenever you're dealing with trig identities, what you need to do is set yourself up a right triangle. Whenever you're dealing rather with inverse trig identities in general. So let's do this here. Make yourself a right triangle, okay? So this sine inverse of x is asking what angle gives you a sine of x. Well, in this case, that'd be theta. Let's make that theta. So the sine of theta is going to be, so opposite over hypotenuse. So what you have now is your sine of theta being x over 1. And we can use Pythagorean theorem to solve for the third side, which would actually end up being the square root of 1 minus x squared. Alright, so let's rewrite this side here. So we have the tangent of the sine inverse of x. Well, that's going to be the same thing as the tangent of theta. Well, now what is the tangent of theta? So opposite over adjacent, that's going to give you x over the square root of 1 minus x squared. We've just verified the identity. So therefore, we can say that the tangent of the sine inverse of x is equal to x over the square root of 1 minus x squared. And whenever you're dealing with inverse trig functions, go ahead, set yourself up a right triangle. That's going to be a lifesaver to help you verify, because otherwise, how are you to know this? The right triangle is really going to help you. I should probably put a right angle here just to denote that it's a right triangle. Alright, now I got 3 more of these, and then we will move on to the final phase of the lesson, which will be doing trig substitution. I'm going to keep the triangle up, but let's see what we got next. Now we got to verify that the cosine of the sine inverse of x is equal to the square root of 1 minus x squared. So we're being asked to verify that the cosine of the sine inverse of x equals the square root of 1 minus x squared. So again, let's deal with the left-hand side. The cosine of the sine inverse of x. Now, what angle gives you a sine of x? That's going to be theta. So the sine of theta is x over 1, or otherwise x. So we can rewrite this simply as the cosine of theta. Well, the cosine of theta, first we need to find the third side using Pythagorean theorem. Again, that would just be the square root of 1 minus x squared. So to find the cosine of theta adjacent over hypotenuse, what do you know? You just get the square root of 1 minus x squared. So we've just verified the identity. So therefore, the cosine of the sine inverse of x equals the square root of 1 minus x squared. So these inverse trig functions really aren't that bad. They look horrendous, but I promise you, they're really not that bad. And these come up all the time in calculus as well. Okay. This is going to be a fun one. We have the tangent of the sine inverse of x minus 1 over 4 is equal to x minus 1 all over the square root of 16 minus the quantity of x minus 1 squared. All right, so we have a little bit of a doozy. We have the tangent of the sine inverse of x minus 1 over 4 equals x minus 1 over the square root of 16 minus x minus 1 squared. Well, let's write out the left-hand side first. So we have the tangent of the sine inverse of x minus 1 over 4. Okay, this is asking you for the sine inverse. What angle gives you a sine of x minus 1 over 4? Well, again, that's theta, so the sine is x minus 1 over 4. And we can easily solve for the third side by the fact that we can use Pythagorean theorem. So, what do you know? Using Pythagorean theorem, you would get 16 minus the quantity of x minus 1 squared. So all of a sudden, this isn't so bad. So this left side would just simply turn into the tangent of theta. Now, what is the tangent of theta? So that's opposite over adjacent. Well, that turns into x minus 1 over the square root of that 16 minus the quantity of x minus 1 squared. So we've just verified the identity. So therefore, the tangent of the sine inverse of x minus 1 over 4 is going to be equal to x minus 1 over the square root of 16 minus the quantity of x minus 1 squared. I got one more of these, then we're going to do 4 trig substitution types, and then we'll be done with the lesson. Let's erase that. What do we got here? Finally something different. So we're going to have the tangent, this time of the cosine inverse of x plus 1 over 2 we have to verify that that's equal to the square root of the quantity of 4 minus the square root of 4 minus the quantity of x plus 1 squared all over x plus 1. Okay. So let's write out the left-hand side again. We have the tangent, this time of the cosine inverse of x plus 1 over 2. So inside the parentheses here, this is the same thing as saying what angle gives you a cosine of x plus 1 over 2. Well, that's going to be theta. Cosine is adjacent over hypotenuse, so adjacent is that x plus 1, hypotenuse is 2. And then we can use Pythagorean theorem to solve for the missing side. which, what do you know? That's going to be the square root of 4 minus the quantity of x plus 1 squared. So this can be rewritten simply as the tangent of theta. Now we can just find the tangent, which is opposite over adjacent. That's going to give you the square root of 4 minus the quantity of x plus 1 squared, all over that x plus 1. So we just verified the identity. So therefore, the tangent of the cosine inverse of x plus 1 over 2 is going to equal that square root of 4 minus the quantity of x plus 1 squared, all over that x plus 1. Alright, we're about to enter the home stretch here. We got 4 exercises with trig substitution. Then we should be done. Alright, so sometimes you'll have the trig substitution idea is that sometimes you're going to have algebraic expressions. You know what? In fact, we're going to use x instead of u. Sometimes you're going to have algebraic expressions that, especially in calculus, when you get to integration, are going to be darn near impossible to figure out by using simple substitution. This is where the idea of trig substitution comes into play. So in this case, what we have to do is make x equal to a times the sine of theta. We want to make this whole identity, not just x, but this whole identity equal to a trig function that we can actually manage. So what you need to do now is put that value of x in, substitute that in. So this would turn into the square root of a squared minus a squared sine squared of theta, right? Well, what do you notice here? In the under the radical, you can definitely factor out an a squared. This would be times the quantity of 1 minus sine squared. Alright. Well, this breaks down further into the square root of a squared times the cosine squared of theta. So the value of this whole function, you take the square root of both pieces, you would just get a cosine of theta. So this is going to be something so much easier to work with in certain types of integration problems than this would be. That's this whole idea of trig substitution, and really it's hard to explain more behind it until we get there. But for now, this is just knowing how to use trig substitution as opposed to doing the whole integration process, which isn't till Calc 2. So let's see here. We're going to have a similar problem. We're going to have a squared minus x squared. But this time, a is going to... No. X would equal a cosine of theta. So we're going to do some trig substitution again. So substitute this a cosine of theta in for x. you'll get the square root of a squared minus a squared cosine squared of theta, which would factor this into the square root of a squared times the quantity of 1 minus cosine squared of theta, which would end up giving you the square root of a squared sine squared of theta, which the square root of all that would just be a sine of theta. So this same expression can be written as a times the sine of theta. I got 2 more of these, then we're done. We have the square root of a squared plus x squared. Now, you're going to want to substitute in for x. You're going to want to make that a tangent of theta. X would end up being a times the tangent of theta. So let's substitute that in. So let's stop here a minute. You notice for the past 2 problems you had that a squared minus x squared. Well, what's true with those Pythagorean identities? 1 minus sine squared is cosine squared, or 1 minus cosine squared is sine squared. And that a just happens to be an extra coefficient on it. So that's the idea behind the trig substitution and using your Pythagorean identities. Now, since you have the plus, the reason we're substituting in the tangent is because, well, 1 plus tangent squared would give you secant squared. So we're actually about to turn this into a secant. So substitute that a tangent of theta in for x, you'll get the square root of a squared plus a squared tangent squared of theta, which you can factor out that a squared to start with. You'll get the square root of a squared times 1 plus tangent squared of theta, which now, what's 1 plus tangent squared of theta? That would end up being secant squared of theta. So you'll have the square root of a squared secant squared of theta, which the square root of that would be a secant of theta. So this can turn into a secant of theta. And I got 1 more, and then we're done. And if it's what I think it is, then this won't be that bad either. It's exactly what I thought it was. Okay. So now this time you have the square root of x squared minus a squared. Now, if you have the variable minus the constant, let's think of this identity. If you have secant squared minus 1, what do you get? You get the tangent squared. So that means that a is, or that x rather, is actually going to end up being a secant of theta. The goal is going to be to turn this into a tangent of theta. So let's substitute that a secant of theta in. So you would end up getting a squared secant squared of theta minus a squared. To get the square root of all that, well, you can factor out that a squared. So you would get a squared times the quantity of secant squared of theta minus 1. Well, that secant squared of theta minus 1 just turns into tangent squared. So you get the square root of a squared tangent squared of theta, which the square root of all that would just give you a tangent of theta. So pretty much all the trig substitutions are based on Pythagorean identities, and these come up all the time in calculus. But that's it for this lesson. Next lesson, we're going to apply everything we've learned, and we're going to start solving trigonometric equations, which will be a 2-part lesson. So the next one will be single angle trig equations we'll be solving. So I hope everyone has a great day. Take care.